my 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 foot's really hurting today, so I'm going to try to use the iPad. That way I don't have to walk around as much back and forth. But I'm going to do a quick review, very, very quick review, on what we covered in the last class, which was using organometallic compounds. And in particular, we started off with these organolithium compounds, like alkyl lithium compounds, and then the organomagnesium ones, which had the special name. They were called... What are they also called? So of saying organomagnesium, they call them
the
Grignard reagents. Yes. Grignard reagents. Okay. We didn't really talk about the reason why these are important synthetically. I only tried, the very first year that I was here, we tried to do a lab using the Grignard reagents, but it didn't work well, and so nothing happened. But remember, we discussed that you needed to know how to synthesize them, and that you synthesize them from, if you're starting with an alkane, you have to do a free radical halogenation to make an alkyl halide. But with both of these, you have to have alkyl halides. I can't speak, hopefully. Both of these require alkyl halides in order for them to react, in order to make that. And you use the actual metal, not the salt. So we're talking about 2 moles of lithium metal with the alkyl halide, whereas you just need 1 molar equivalent of magnesium metal with the alkyl halide. And that you have to use solvents such as diethyl ether or tetrahydrofuran, DE or THF. And more importantly, we need to remember that you cannot have anything that has an OH group. Maybe this is going to work. Come on now, stylus. An OH group, an SH group, or an NH group. And the reason being is the fact that each of these have a hydrogen that can be easily plucked off by the carbon of the organometallic compound. In fact, there are even stronger bases than the amine, so you can actually make an amide anion, which is the strong base that we used last semester sometimes, was working with alkynes. Okay, so you can't have any of these in there. So why are these important? This is one way that you can use I don't know why it's not wanting to work. You know what I mean?
You can't use those in any organometallic compound, like reaction or anything?
Right, not with these. And the reason why is, if you remember, these organometallic compounds act like a carbanion, because the metal is much less electronegative than the carbon, and so the carbon's not happy being negatively charged or acting like a negatively charged, and so it's going to go and take off a hydrogen off the oxygen, the nitrogen, or the sulfur. Alright, so you can use these compounds, so the organolithium or the Grignard reagents. Remember, the Grignard reagent usually has a spectator anion, like the chloride or bromide or iodide, something like that, that's alongside just to counterbalance the charge. And I do want to remind you that you will want to go watch the video on the website that goes over how to name these. But you can use these to synthesize alcohols. So you can use them to make alcohols. And so previously we hadn't talked about, last semester we didn't talk about using these to make alcohols. We did a little bit with some substitution reactions, but typically last semester we focused on using alcohols to make other things like alkenes. But here, now we're going to talk about how we can make an alcohol. Now the starting compound that the organometallic reagent has to react with must be an aldehyde or ketone. Okay? Because you're going to start off with something that's already oxidized, and then this carbon is going to be reduced. We're going to see a very similar reaction over and over and over again this semester. So, and remember this, we call this group like an acyl group. It's also called a carbonyl group. So I usually use those interchangeably. That way it can be either an aldehyde or a ketone. Right? Okay, so let's just do like a little generic reaction. This is a mechanism that you do need to know. So this is just a generic mechanism. It's very, very, very simple. So I just have a generic carbonyl group. And I'm going to show it with a magnesium, with one of the Grignard reagents, but it's the same mechanism if you use the lithium as well. And like I said, the X, the halogen is just there. It's the spectator ion. And the asterisk just means that you're supposed to know this mechanism. So what do we have? The first thing that I would do if I were you is let's just review what the dipoles are. So what's one dipole here in this setup? Between the carbon and the oxygen, okay, and what's what there? Right? So we have a delta positive, we have a delta negative. Anything else that's going to be delta positive or negative? And so, I mean, but in what?
Is the halogen delta minus?
So the halogen is going to be negative. Actually, it's usually a fully negative charge, but yes, it's going to be negative. Okay? Or delta minus. What else is there? It's going to be either positive or delta plus or delta minus.
Magnesium can be delta positive.
Magnesium is delta plus. Anything else? Which is more electronegative, the R group or the magnesium? R group, so it's delta minus. That's the whole purpose of these organometallic compounds, is that the R group acts like it's a carbanion. Okay? So it kind of gives it away, but what do we have that is delta minus? Well, that's one reason why I say put this delta minus or negatively charged. I can do the attacking. The R, and it's going to attack rather than the X. Yes, the X may be negatively charged, but it's happy. Remember, chloride, anion, fluoride, iodide, those are actually relatively happy being negatively charged. That's the salt anion. The R does not like, it likes to be fulfilled. So, what is around that's delta plus or positively charged that it can attack? The carbon of the carbonyl group. So we have boom, sound effects optional. Something has to break or give, because otherwise we'd have 5 bonds around that carbon. There would be 10 electrons around it. So something has to break or give. The double bond does. And so I'm going to show it this way, where one, it doesn't matter which one, and it goes up towards the oxygen. And so we're going to see this, like I said, this semester. The mechanisms aren't that bad. For the most part, you're going to see the same type of thing over and over and over again. Those who are in biochemistry, you've actually been doing this kind of thing last semester and this semester, so it's nothing new.
Did you say that, like, right now we're doing an example of, like, I don't know how to say it right, but, like, Grignard. But you said
Grignard,
it could be the same process for the organolithium.
Mm-hmm. It's just because the lithium's delta plus, the R is delta minus. Mm-hmm. Exactly. So now we're just going to draw the product or products. So we still have the carbon that got attacked, but now it has 4 single bonds around it. I'm going to draw it this way, showing the lone pair electrons around the oxygen, so it's going to be negatively charged. And the R group of the Grignard reagent or the organolithium reagent is now covalently attached. The magnesium halide are now, they're just spectator ions. So we have a magnesium that's positively charged. Technically it's going to be a 2 plus charge, and an X that's going to be a minus charge. I'm just going to show them right there. You know, they're going to be attracted to the oxygen, but it's not like a covalent bond or anything like that. And so we went from a trigonal planar carbon to one that's tetrahedral. Right, so this is now a tetrahedral carbon, whereas we started off with the trigonal planar. But we said the whole goal here was to make an alcohol. We haven't made an alcohol. Does anyone remember what this is called whenever it's an alcohol that doesn't have hydrogen? Has to end in ite, or, well, those are the biggies, or ate. What is it called when alcohol loses its hydrogen? This is just a generic name. It's going from an alcohol to an alkoxide. Okay, so we've made an alkoxide, but we want to turn it into an alcohol, usually. And so to do that, what are we going to add to the reaction, to end this reaction into? How do you make an alkoxide and turn it into an alcohol? What are you adding? Hydrogen. And how do we add hydrogens? You just can't stick hydrogen metal in there. No, I mean, it's really simple. Like, just how do you add hydrogens? Yeah, it's protonation. So you just add an acid. So I'm just going to do it as a generic H3O+, but you know, sulfuric acid, HCl, doesn't matter. It's just an acid.
If it's an alkoxide, it was an alcohol prior then?
No, an alkoxide is just an alcohol that doesn't have a hydrogen.
Oh, okay.
So now we would have the alcohol. That's supposed to be an R, but I'm running out of room. All right. So now we have an alcohol. So we've gone from a ketone or aldehyde. We've gone from a carbonyl group to an alcohol. But remember, in order to make it an alcohol with this, you have to have a final step when you acidify it. You lower the pH. So that way the oxygen takes the... And I mean, the mechanism for that is one that we've already seen in the past. You know, the oxygen's negative. It takes one of the hydrogens. That kicks off of water. I just don't have enough room to write it all out like that. But that's, I mean, we've seen that kind of thing over and over again. It sounds like they're really happy next door. So now let's do some specific examples. We're going to start with formaldehyde, which you haven't learned how to name. It's also called methanol, but more commonly it's called formaldehyde.
What is the name of this mechanism?
It's a generic one for any of the organic.
Right. And so,
Lighter ketones.
right, it's just a... I mean, you could say that it's a, I don't know, nucleophilic attack using, organometallic compounds.
You're synthesizing an alcohol.
I would just say like synthesis of an alcohol from, aldehyde ketones. You'll find out that it's not the only way to make an alcohol from aldehyde ketones. Notice you're going to always make the product will always be bigger than what you started off with. So if you start off with one carbon, it's going to have more than one carbon in the final product. So there will be times later on in the semester, like actually the next chapter, where we may want to make an alcohol that has the same number of carbons, and you don't want to use this because there's no way to do that. But if you're starting off with something that's small and you want to make a bigger alcohol, this is a way to do it. So this is formaldehyde, which is nasty, nasty stuff. Okay. And now I'm going to just do a specific example here. We're going to use something that's very simple, just because I don't have a lot of room to write. And so we're going to use methyl lithium. Okay. And what solvent or conditions do we need to do this in?
For making an alcohol.
Right. I mean, well, using organometallic compounds, what solvent are we going to be using? THF or DE. I'm just going to write DE here, but it could be THF. Oh, come on now. DE because I don't have to write as many letters. But that stands for diethyl ether. And I'm going to give you a moment to draw out the mechanism yourself. And for this specific example, you should even be able to name the final product. Okay? I'm going to pause this. Okay, so what do we have here that's going to be doing the attacking?
CH3.
The CH3, the methyl group, is going to do the attacking. And what will it attack? The carbon of the carbonyl, boom. And something has a break or give. Double bond breaks. So then we are left with H, C, CHO minus CH3. And then to convert this all the way into the alcohol, we have to add some type of acid. I'm just going to write down HCl here to give an example, specific example, but you could write H3O plus. That's fine. And so, what would be our final product?
So you get ethanol?
You get ethanol. Yep. Ethanol. So please note, in order to make a primary, so right here we made a primary alcohol. Overall, in order to make a primary alcohol, you have to start off with formaldehyde. Okay. So if you're wanting to make a primary alcohol, the ketone or aldehyde that you have to start off with is formaldehyde. If you have anything else, it won't make a primary alcohol. Let's do another example.
Wait, so it can be another type of ketone?
Not if it's going to be, and not if your final product is wanting to be, because let's see what happens here. Whoops. So you don't know how to name this yet. You'll find out. This would be called butanal. But that chapter comes later on. And this time I'll do a Grignard reagent to show that we don't have favorites in this class. And THF. And so I'll give you a moment to work through the mechanism. Okay, so now what do we have? It's going to be delta minus or negatively charged. I can do the attacking.
Benzene ring, the extra carbon.
Right. It's going to be the carbon that's attached to the benzene ring, which is called the benzyl carbon. Okay, so, and what will it attack?
The carbon on the double bond.
Right.
Carbon
Boom, boom, because we have to break that. Draw everything that, first of all, you draw everything that did not change. So we have, if you notice, we have this carbon, 1, 2, 3, 4 carbons. So 1, 2, 3, 4 carbons. And that carbon is now going to have an O minus attached to it. And technically the magnesium bromide would be up there to help offset the charges, but I'm not going to draw that for clarity's sake. But we now also have one more carbon that did the attacking and the benzene ring. Whoops, I drew my benzene ring wrong. One more carbon. Someone's got some national pride over there. Okay.
Are we supposed to know how to name the final product?
Yes, on this one you can name it as well. And then what would we do?
Add acid.
You add an acid. This time I'm just going to say H3O plus. And draw 1, 2, 3, 4, OH. So OH. Another carbon. Benzene. What gets top priority in naming, the alcohol or the benzene group?
Benzene.
The alcohol. Okay, and so then we have to look to see, well, what's the longest carbon chain for the alcohol? 1, 2, 3, 4, 5, right? And so what kind of alcohol would that be? So it'd be pentanol, right? And so we put... You can either put the number locant after the N, or you can put it before the P in pentanol, since there's not like a double bond or anything like that. I'm going to go ahead and put it before the P, just because I didn't leave myself much room. So we have to give a locant for the alcohol. What number is it going to be? 2, because it gets top priority. Then what is a benzene ring whenever it's directly attached called? No, whenever it's directly attached, it's called a phenyl group. And so this would then be phenyl. Whoops, the N did not come through. Let me give myself a little bit more room. Phenyl, and yes, it's one. So 1-phenyl-2-pentanol. Now, if there's a linking carbon between the benzene ring and whatever the main carbon chain is called, it's called a benzyl group. But here, the benzylic carbon is actually a part of the long chain, so it's a phenyl group. So for those of you in biochemistry, just think of alanine, and when you put that benzene on the alanine, it becomes phenylalanine. So that's how I do it. We'll have more examples of phenyl versus benzyl, especially when we start naming like esters and amides and things like that. Okay. So let's do another example. Oh, I forgot to point that. I wanted to point out here that in doing all of this, we made, what kind of alcohol do we make here? Primary, secondary, tertiary. It's a secondary. So to make a secondary, you have to start off with an aldehyde that touches one other carbon. You can't use a ketone. So let's go ahead and do something. This is cyclopentanone. You don't know how to name it yet because we haven't done aldehydes and ketones. I'm going to go back to lithium because that way I don't have to write as much. NDE.
Is that an O?
No, that's a carbon that has got a little out of hand. That's just a carbon. I was trying to make sure that you can see that there are two carbons there. So that's ethyl lithium. Right, so not to sound like a broken record, but what do we have that can do keep seeing it over and over and over again? So like they say, if you see someone's name 3 times and you meet them, they'll stick in your mind. So if we keep saying this over and over again, maybe it'll stick in your mind. But what do we have is a delta minus or negatively charged that can do the attacking? The R group that's directly attached to the metallic group, which is lithium in this case. And what can it attack? What's going to be electrophilic for it to attack? The double bonded carbon. And so let me switch my colors. Boom. Boom.
Does that carbon have a special name, like the benzyl carbon?
The acyl carbon?
That was
Or the carbonyl carbon? So let's draw the cyclic, whoops, that's supposed to only have 5 carbons in it. The cyclic pentane doesn't change at all. Okay, then we have the alkoxide anion that's attached, and we have the ethyl group that's attached. And once again, the lithium would be there to counterbalance the charge, but I'm just not drawing it in since it's a spectator ion, and also just because of clarity's sake. So we've made, I was about to give away what happens in future chapters, but we've made a tetrahedral carbon. Then if we want to turn this into an alcohol, then we have to add, right, you have to protonate. H3O. I don't know why it does that sometimes. O plus. And so now I'm going to draw it down. I'm going to draw it down here. This cyclopentane group, the OH, and that. And so what would the name of this be? Right, so 1-ethyl 1-cyclopentanol is good. Technically you could get by saying 1-ethyl cyclopentanol because by default, since there's only one function we're paying off of it, by default the oxygen has to be on carbon number 1, but you won't get in trouble if you say 1-ethyl 1-cyclopentanol or 1-ethyl cyclopentan 1-ol as well. Which just becomes kind of wordy. But I want you to notice what kind of alcohol did we make here? We made a tertiary. So if you start off with a ketone, you're going to make a tertiary alcohol. And remember, there isn't such a thing as a quaternary alcohol because that carbon would have too many bonds. I already have a video on the website, I think, on how to do alkane synthesis using organocuprate reagents, but I'll briefly go over it here just quickly before we start doing some retrosynthetic analysis.
Is that the video that you're referencing to last class to watch them?
No, that was naming.
Okay.
So yeah, I had to name these, which the naming is really easy, but both of them's on the website already.
For this for this tertiary alcohol that we made, we said to start off with what?
You start off with a ketone. Because that carbon, the acyl carbon's already touching two other carbons, you're adding a third. So that's why you just have to realize whatever you're wanting to make in the end the beginning has to have one less carbon on it.
Okay. What was the secondary then? It was aldehyde.
And an aldehyde that has touched one other carbon. And to make a primary, you have to have formaldehyde. That's the only way, because it touches two hydrogens. All right, so this, once again, this is kind of wordy, but it's alkane synthesis. Oh, not that. Synthesis. Using organocuprate, which cuprate is what element forms cuprate ions? Copper. So I'm just going to say Cu here because I'm running. Reagents. You do not need to know the mechanism for this one. Okay. You just need to know the reaction conditions. And like what it's going to form, like what is.
So we're using alkene to synthesize an OM?
Pardon? No, you're going to use organocopper reagents essentially, which is another type of OM to make alkanes.
Okay, so you're
So what you're going to do is you actually need to start. Well, I mean, you can start with a smaller alkane to make a larger alkane, but we're going to actually kind of skip ahead to where you start with 2 molar equivalents of an organolithium reagent. So see, we already know how to make the organolithium reagents. And this time we're not using the copper metal, like copper wiring. You're not using that kind of copper. You actually are using the copper salt. So like copper chloride, for example, copper 1 chloride. Again, we have to use DE or THF. Once again, I'm writing DE, but it could be or THF. Just you can't have it around something that has an OH, NH, SH, something like that. And you're going to form an intermediate first. Okay, this intermediate, I'm going to just draw a generic one first because it's something that we haven't seen before. All right. It's a lithium dialkyl cuprate ion, which is a mouthful. So this is what happens, but you don't need to know this mechanism. This is just to try to explain. You could probably figure it out if you thought about it enough. I don't know why it's not wanting to work. So we have that, and we've got copper, say for example copper chloride or copper bromide. Just knowing what you know about the organolithium compound, what is delta minus or negatively charged that can do the attacking? The R group, and then what on the copper halide is going to be positively charged? The copper. And so it just goes and it smacks the copper, kicks off the X, essentially. Oh. So now we have the copper attached, but it doesn't stop here. And a lithium salt. I'm just not going to show the lithium salt right now, because this is where the second.
So is that the lithium came off?
Yeah, the lithium is just a spectator ion. The first lithium is a spectator ion. The second lithium, because this is the reason why it takes 2. So what happens now is that we just repeat this with the second equivalent, where it attacks. There's nothing that leaves, per se, here. But what we form, I'm going to have to draw it down here, if you don't mind, because I don't have much room. Looks like this. It's an R, because if you remember from Gen Chem, copper can have more than one oxidation state or more than one charge. It can either be +1 or +2. And so this time, the copper went from being a +1 to a +2. So it actually holds on to 2 of the R groups. And the copper, overall, all of this is negatively charged. And then we have just the lithium as a cation. It's a spectator ion. That's why they call this a lithium dialkyl. So, for example, if the R groups were ethyl, it would be lithium diethyl cuprate.
So why does the R group turn the second lithium, the R and lithium group, want to attack the copper? Would it still be? Because wouldn't the R group not change the charge on delta plus and delta minus, or?
Well, the first R group is fine. It's the second R group that comes in. It's going to be. That's why it takes 2 R allies, 2 OMs, 2 organolithium reagents. The first one attacks first. The second one then comes in and attacks the second time. So this is just the intermediate. Okay. So now I'm just going to draw this part. Once again, you just need to know the overall reaction conditions. So we made the intermediate, this is really messing up on me. I think I may need a new stylus. So the intermediate, whenever you abbreviate it, write out the chemical formula, it looks like that. Plus, and I'm going to just say, I'm going to use R prime, but it's another alkyl group. Oh, whoops, not that one. And it's a halogen, so I'm just going to use iodide. But it's an alkyl halide. You have to do this once again like in DE or THF, because otherwise your alkyl groups, the ones that are delta minus, will attack the solvent if you use water or ammonia or something like that. And they typically do this at low temperatures. And in the end, what you're going to get is one of these R groups, only one of them, is going to connect with the second alkyl halide. And so what you're going to get is this. R prime plus, and you still get an RCU, which could be used if you have additional organolithium reagent. It can be used again. Okay, so this is just one way to make an alkane. We don't have very many ways to make alkanes. Last semester we talked about how you take something like an alkyl halide, you turn it into an alkene, and then you do hydrogenation to make an alkane. But this is just another way to do it. It gives you another reaction to use in your handy-dandy tool belt. Alright, so let's do some retrosynthetic analysis, which is just a fancy way of working way backwards. You're given, for example, you're given the final product and you have to figure out how you can make it. So for these kind of questions, some people really like them because there's more than one right answer. Some people really struggle with that because they don't like the not knowing, not having a concrete yes or no. These are carbons. I'm just making it. So here we go. So this is 2-methyl-3-pentanol. And our goal or challenge is we need to figure out how we can make this from an aldehyde or ketone. So you want to work backwards. What's the last step of using organometallic compounds? Protonation. So we know that that's going to be the last step. So there's H3O plus. So just draw what it looks like without the hydrogen. 1, 2, 3, 4, 5. Okay. First of all, we already have the choice of using organolithium or Grignard reagents. It doesn't matter which. But now the question is, what did the original aldehyde or ketone look like? And is there more than one possibility? Or are there more than one possibilities?
Well, it would have to be double bond, like the oxygen would have to be double bonded to that carbon.
Exactly. So this is the carbon that got attacked.
Yeah.
All right, so that's why what we're going to do is just draw that. Because remember, your arrow is going to go backwards since we're working backwards. And it's fine with me if you want to draw it like in an atypical way. No, normally when you draw aldehydes or ketones, we have the oxygen pointing up. They don't have to point up. They can point left, right, down. It doesn't matter. Then we just have to look at one side or the other. It doesn't matter. That's why there's more than one correct answer. I'm going to choose to look at it this side. Just because I use my right hand this time. This is how I'm right. And so unless you're told otherwise, it doesn't matter. So that means that the carbon that got smacked, was attached to 2 other carbons. Oh, whoops, I forgot to change my pen. It was attached to this. So that was the aldehyde or the ketone, which that's an aldehyde, that got attacked. Now we have to look to see how many carbons was in whatever did the attacking. There's 3, because you now look at the other side of the ground zero carbon. And so, and we know it had originally, whoops, didn't mean to do that. I'll do it in a different color. So there were 3, maybe it's going to come up, there we go, 1, 2, 3. And which of those 3 carbons had to have the, I'm going to say lithium this time, the lithium attached to it? The second one. Now, if the question said go all the way back to the alkyl halide or alkane even, then you could work backwards and say the alkyl halide would have been like 2-chloropropane, would have been an acceptable answer. Or propane, if you go all the way back to the alkane. You can make propane into 2-bromopropane or 2-chloropropane to the organolithium. We attack it with, well, what we'll find out is 1, 2, 3, propanol. And then, and we don't want to forget the reaction conditions. So what solvent could we use here? Okay, well, I heard TE and THF and DE, but yeah, either one. Okay, so there we go. That's it. That's one possible answer. The other possible answer is just do the other side. Okay, so rather than have 3 do all of it, I'm just going to erase this part. Work backwards. So they're all the ground zero carbon with the oxygen, but now we're going to be looking at that. Make sure it's the same on your the left-hand side, and it's attached to the 3 carbons, like that. Let me switch colors. This is the side that did the attacking, and so how many carbons was on it? 2. And this time I'll just say it's the Grignard reagent, just so that way we show that we don't have favorites. And then once again, if it asks you to go all the way back to the alkyl halide, here it would be bromoethane. If it asks you to go all the way back to the alkane, it could be ethane. Ethane became bromoethane then became the ethyl magnesium bromide, which then reacted with the aldehyde that you see here, and then goes on and on and on. So that's why with these, there's almost, unless they're given certain restrictions, like sometimes you've seen questions in the book where it says, nothing can have more than 3 carbons, or something like that, then you have more than one possibility. But, Okay, are there any questions?